Good morning, good afternoon, and good evening. This is proposal number 4 to the Trust over IP Trust Spanning Layer Protocol Task Force. Previously, we've heard about proposal 1 from Sam Smith, proposal 2 from Daniel Hardman, and proposal 3 from Wing Jing. This was originally intended to be a lightweight response to Daniel Hardman's proposal number 2, and it's turned into a full-fledged, highly detailed explanation of the Web 7.0 Trust Spanning Layer Framework, hence the designation ++. My name is Michael Herman. I'm a self-sovereign blockchain architect and developer, and founder of the Hyperonomy Digital Identity Lab, from which the Web 7.0 project has been given birth. I live on a cattle ranch in Alberta, Canada, and those are some of my cows. Why have a Hyperonomy Digital Identity Lab in Alberta? Because there's lots of information, lots of relationships, lots of different kinds of identifiers that we use for the land, we use for the cattle, we use for our businesses. Although I'm recording this in the middle of the night, when I wake up in the morning, this is the view out my office window, my home office window. So just a couple prefaces here before we get started. One of the things you'll find in this presentation in particular is you'll see a number of existing concepts being recast in different ways. I have a compulsion, if you will, to break things down into their basic elements and the ability to synthesize or reassemble them from the ground up. And that concept is called first principles thinking. You'll see that executed over and over again in this talk. And I don't really apologize for it. This is another interesting post from my blog. This is back in 2019, actually, February 2019, so 4 years ago. Sam Curran was there talking to a small group of developers about the importance over the course of history for Internet protocols not only to be open, but more importantly, open to innovation. Innovations that might succeed as well as innovations that might fail. And his exact quote talking to this small group in Vancouver was, if you look at important internet protocols like TCP/IP that enable packets on a network to carry any type of data, including text and email messages and web pages, etc., and then later on, streaming video and streaming audio, who could have imagined this scenario? It's vitally important that internet protocols not only be open, but they be open to innovation. Innovations that might succeed as well as innovations that might fail. No one can foretell how the specifications we're creating today will be used in the future. How this is relevant here is that I'll be talking a lot directly and indirectly about the DID communications or DIDCOM protocol. And I believe it is one of these fundamental protocols, just like TCP/IP. And it will be used for purposes we can't even begin to imagine for decades and decades to come. So as a bit of a background, I'm just going to go through these really quickly. I've been working on message passing based systems since 1986. If you are a Microsoft Windows historian, you'll recognize this as the very first Microsoft Windows 0.989 SDK sample called generic.c. And it's all about dispatching messages in Windows. It still compiles and runs in Windows today. I've worked on a lot of architecture reference models. Here's the famous Alice buys a car scenario from the Hyperledger indie days. A lot of Web 7.0 was inspired by a decentralized platform that came out 20 years ago. in 2000 called Groove Workspace, created by Ray Ozzie and his awesome team at Groove Networks. Here's a shot of the Sovereign glossary, a complete model of every term in the Sovereign glossary. So every term that is used in Hyperledger Indy to describe the Sovereign platform. Many, many more architecture reference models, languages for working with DIDs, more architecture reference models. This is the Hyperledger Aries 004 RFC, written by Daniel Hardman, who continues to be a great mentor today, where we started to categorize this concept of agents, decentralized agents. Lots of architecture reference models for the Microsoft platform. Lots of models for the Enterprise Data Vault and DWN world. Created a DIDCOM protocol. And so that brings us to the agenda. So I've worked on a lot of different things over the last 5 years. The key overarching project is called the Trusted Digital Web, which in turn has given birth to Web 7.0. And so I'm going to use that, well, decades of experience and the most recent 5 years to talk about something I call Proposal 4. And we're going to do a little bit of background and look at some examples so that we're all kind of on the same page. Giving a presentation like this is like going on a bus tour. The most important thing, the very first step, is to get everybody on the same bus, and that's what we're going to do in steps 1 and 2. And then we're going to go into more details. It's partly a proposal to the Trust over IP, Trust Spanning Layer Protocol Working Group, but it's also just the most detailed explanation I've ever provided of the Web 7.0 Trust Spanning Layer. So we'll look at that in a series of steps, as you see under number 3. And then I think this is the first time the Trust Spanning Layer Protocol Assessment, the Trust over IP Layer 2 Trust Spanning Layer Protocol Assessment for DIDCOM has been published. This is actually not my work. Brian Richer and Daniel Harbin contributed to this. I nudged them a little bit to finish it up, and I did a little bit of formatting, and you'll see that being presented here at the end. I'll leave it to the very end to tell you what the conclusion is of that assessment. There is a lot of detail in this presentation, referring to the footnote, but the goal is to actually present these concepts at an awareness level. If you want to learn a lot more about what I'm talking here, refer to the Web 7.0 white paper, and you'll find that at hyperonomy.com, just like it sounds, hyperonomy.com. It's pinned to the top of my blog. And one of the taglines for Web 7.0 is take what you need and leave the rest. So there may be things you like here, there may be things you don't. Take what you need and leave the rest. So an important part of background is the DIDCOM architecture reference. And that's what's described in the Web 7.0 architecture white paper. The cover page that you see here was written over the course of 4 or 5 weeks, starting on a trip home on November 24th, 2022, on a flight from Amsterdam to Calgary, Alberta. Everything, all the intellectual property is copyright under the Creative Commons with Attribution International Public License that you see highlighted here. This white paper is neither a W3C, DIF, Sovereign Foundation, or Trust over IP Foundation Public publication. It is a sole independent product of the author. It has no official, unofficial, or otherwise relationship to these groups. This is the all-in kitchen sink model. We're not going to go into any depth on this eye chart, but the idea is the focus is on DIDCOM clients and DIDCOM agents, and how DIDCOM communications is used to communicate between them, how messages can be routed through a network of DIDCOM agent-based message routing agents, how the DID registry is implemented and architected in this system, concepts of anthropomorphism and personification. There is a YouTube playlist for W7.0 and the DIDCOM architecture reference model, and I refer you there for more details. Part of the first part of the Web 7.0 white paper goes into something, it describes in reasonable detail something called DIDCOM notation. Knowing in advance that I needed to produce a large number of diagrams over the course of writing that white paper and on into the future, and having a background as an enterprise architect, familiar with the Archimate enterprise architecture modeling language, I knew that we needed something, and this was going to be a very important contribution to the DIDCOM community. So let's have a look at what DIDCOM notation is, and we're going to use it throughout the rest of this presentation. So the cornerstone of DIDCOM notation, of course, is a DIDCOM agent. And you see coming out of the bottom of the DIDCOM agent two interfaces. There's the one on the left labeled outbound processing with an arrow. That is a little bit unconventional. That is what we call an origin interface formally in the DIDCOM ARM, and that's where messages come out of the agent. It's that little piece of code that you have that will, invoke the HTTP client, an instance of the HTTP client, and do a get or a post operation for sending messages out of your agent. And on the right-hand side, we have the corresponding inbound processing. So that's the classic service endpoint that agents are expected to have. And the purple boxes refer to special kinds of processing that we do on the inbound processing sides, and the special kind of processing we do on the outbound side. On the outbound side, we need to do auth encryption, for example, and any other additional types of processing that are required. We're going to go into a lot of detail in terms of what's happening in the purple boxes. So inbound processing is used to receive DIDCOM messages. When a DIDCOM message is received, it's decrypted, it's authenticated, and then typically processed by a workflow running inside the DIDCOM agent. Outbound processing, as I said, is used for generating DIDCOM messages. And here, these two particular styles of purple lines represent DIDCOM messages. The sheath represents the fact that it's an auth encrypted message. It's not just a plain old text message being sent by, as a REST over HTTP message. And of course, any of those messages that emanate from an origin interface, from an outbound processing interface, are received by a fellow DIDCOM agent. So here we can see the agent on the right is performing creating an auth encrypted DIDCOM message. It is sending that message over whatever transport your particular platform uses. DIDCOM is transport agnostic, to the inbound processing interface of, in this case, the receiving agent on the left-hand side. These are the most basic and holistic principles that comprise the DIDCOM communications protocol. So we're going to look at this in a little more depth. And we're going to add a couple more names. So that agent on that right that does outbound processing and creates the message, does the auth encryption, and sends the message out is called the sender agent. So the sender agent's on the right. The receiving agent here is on the left. We send DIDCOM messages over whatever transport. In this case, for most of the examples here, we're going to use HTTP, but it could be gRPC, it could be WebSockets, it could be plain old sockets, it could be whatever you want to use. It could be email messages. It could be dial-up networking. But this is the classic scenario, which we refer to as the sender-receiver model. And the title of this slide is Verifiable Credential Sender-Receiver Model. And that's referring to the ability of a DIDCOM message to carry embedded in it, or as an external reference, any sort of attachment. So in this particular case, we're showing a business card represented as a verifiable credential being sent as an attachment along with this DIDCOM message. This is the core building block. This is the Lego piece that has, the 8 dots on the top on which we're going to use to build everything else. This slide isn't really intended to be part of the deck, but this is my palette of DIDCOM notation symbols. This is the first slide I add to a new deck, and this is the palette from which I pick up DIDCOM agents or REST agents or personifications of agents like ABC Grocery or the Thrift Bank or David's Cabbages there at the top. There's icons for DID registries. There's icons for host computer systems. There's icons for DIDCOM network message router agents, DNS servers, everything that you need to architect, design, and implement a decentralized system. So this is referred to as the DIDCOM notation palette. Okay, so we know a little bit about the DIDCOM notation. These drawings then won't seem so strange. So we're going to look at some examples. These are actually live demos that we're preparing for IIW 36 in a couple months here to demonstrate the Web 7.0 DIDCOM architecture reference model, and the part of the architecture reference model is the Web 7.0 trust spanning layer framework. So here's a simple chat program. Across the top, we see 2 DIDCOM user agents. One is Alice's, one is associated with Alice, and one is associated with Bob. A user agent is different from an ordinary DIDCOM agent in that a DIDCOM user agent has a user interface, a user experience. It's the way that a person can interact with the DIDCOM network of other agents. So we have Alice, for example, here, has typed something into her DIDCOM user agent, this chat program. That piece of text, that message, represented as a DIDCOM message, is being sent down to the DIDCOM agent her user agent is paired with. We see that on the right-hand side here in the blue box. And that user agent then at the bottom of the blue box is sending that over to Bob's agent because it's addressed to Bob. It uses Bob's DID, and Bob's agent receives that on its inbound processing interface, and then from its origin interface, from its outbound processing interface, it's sending that up to the UI, to the user agent, in the green box, top of the green box. So why do we have 2 DIDCOM agents? Why do we have user agents and ordinary DIDCOM agents? Imagine the user agent is a lighter weight agent that runs on your phone. And imagine the DIDCOM agent, the regular DIDCOM agent, as an agent that's running in your home or your office, or perhaps in a data center. That's where your entire life lives. That's where your entire collection of data and objects and entities and certificates and verifiable credentials live. They live in the DIDCOM agent at the bottom of the green box and the bottom of the blue box. Some of them will be requested or retrieved by the user agent, but simply for the display purposes on your particular device, your tablet, or your handheld phone. On the right-hand side here in the yellow box, we have the DID registry, because we know that TCP/IP today and HTTP today don't understand DID addresses. The DID :person :5678 that is Bob's DID. So we need to be able, Alice needs to be able to look up Bob's DID, the DID :person :5678, needs to look it up somewhere and get what's called the DID document. And in that DID document will be the URLs for Bob's agent. In this case, the bottom of the green box, we can see that the URLs that are in that DID document for DID :person :5678 is http://example: 8085. And once Alice's agent has made that query, or more correctly, it's Alice's agent has made that query to the DID registry, it can then create the DIDCOM message. It might add an attachment to that DIDCOM message, and then it can send that over as an HTTP put to Bob's agent to be subsequently displayed on Bob's user agent. Of course, we're talking about trust spanning layers, and trust spanning layer singular, and trust spanning layer protocol. So the green line here that connects Alice's DIDCOM agent to the DID registry, you notice that actually is running over DNS. I won't explain that any further, but it is running over DNS. So if we're talking about and truly believe in the concept of a trust spanning layer protocol, why don't we use DIDCOM to also query the DID registry? So we have the concept of the DID registry gateway. It's a DIDCOM agent, a specialization of a DIDCOM agent. Just like the user agent is a specialization of a DIDCOM agent, the DIDCOM registry gateway agent is also a DIDCOM agent. And its sole purpose is to take queries, DIDs, incoming DIDs, and transform those in incoming DIDs over DIDCOM and transform those to be the same DID queries, but running over DNS. So it's really, the gateway is really a transport level gateway, changing the transport protocol. When the gateway receives the DID document back from the DID registry, it repackages it as a DIDCOM message and sends it back to Alice's agent. Alice's agent then is going to use the service endpoints in that DID document to send the information to Bob, as we described earlier. So you're starting to see this concept of a trust spanning layer protocol applied in a very pure way. In Web 7.0, everything runs on DIDCOM. DID resolution, as we see here, runs over DIDCOM. The DIDCOM network message routing agents also run DIDCOM. We're just embellishing these demos one slight step at a time. So in the previous slide, we saw how the DID registry was used to look up the, Bob's DID, how Alice was using the DID registry to look up Bob's DID and to send a message. Now we're sending a message, but we're attaching that business card verifiable credential. So this is the only small incremental change we're seeing here. In all the previous examples, Alice's DIDCOM agent spoke directly to Bob's DIDCOM agent, peer-to-peer. If Bob's agent was not running, or it was behind a firewall, it would be impossible for Alice's agent to talk to it. So this is where we introduce the concept of the DIDCOM network message router agent. Here I'm showing a singular agent in the green box, and its purpose is to route messages, do intelligent message routing between the sender on the right and the receiver on the left. It's an example, again, of a specialization of a DIDCOM agent. Just like the DID registry gateway agent is a specialization of a DIDCOM agent, so is a DIDCOM network message router agent. And in this particular example, what its purpose in life is to be a relay agent, like in the Groove Networks platform. When Alice tries to do a direct point-to-point DIDCOM message transfer to Bob and is unable to, then what Alice will do is look up the DID for the nearest DIDCOM network message router agent, and it'll send that message intended for Bob. It'll forward it, to use DIDCOM terminology. It will forward it to the nearest network message router agent. In the fullness of time, there won't be just a single network message router agent, but there'll be an entire interconnected graph of DIDCOM network message router agents. And that's what we're showing in this next diagram. So down here at the bottom in the yellow box, all of those blue dots are DIDCOM network router agents, message routing agents. And they support, just like TCP/IP routers at the Internet Protocol level, route TCP/IP packets. The role of the DIDCOM network router agents is to route DIDCOM agents in the same way. The scope of, or the description of how that intelligent routing takes place is analogous to what happens in TCP/IP, but the description is out of scope for today's talk. So we started with just a very simple scenario of two agents talking to each other, directly to each other, and we used the DID registry in the green box to look up DIDs and to find service endpoint URLs to facilitate that message transfer. And then we extended that simple point-to-point message transfer with a relay agent, with a DIDCOM network message routing agent, and then we extended it to a large interconnected graph that will form a global message passing and delivery network. But all of that, and including how DIDCOM agents talk to DIDCOM user agents, it's all DIDCOM. So what we end up with is a very simple building block, the variable credential sender-receiver model. Sender agents create messages, attach whatever payload. It doesn't have to be a verifiable credential. It could be an MDL driver's license. It could be a PDF file. It could be an XML document. It could be a Microsoft Office Word or spreadsheet document. Whatever the payload is appropriate for the business application, the business protocol that you're trying to implement. We can attach those to DIDCOM messages, and we do all of that in the purple box there on the outbound processing side. We typically use HTTP over REST, the REST over HTTP as the protocol to send it over, but again, it could be Bluetooth, it could be whatever. And that's received on the inbound processing side of the receiving agent, receiver agent. And this is the simple principle upon which all of Web 7.0 is based, and that I'm advocating becomes the trust spanning layer protocol for ToIP to consider. Okay, so this is the background, and these are the examples that led us to the conclusion that this DIDCOM stuff might be kind of interesting, and it might be an ideal candidate for the trust spanning layer protocol. Let's take it and start to apply it or move it into a more specific trust over IP hourglass model, or in the case of Web 7.0, we call it, we use the Celtic Celtic Tree of Life model. Okay, so this is, I believe, the third part of the presentation. Again, from a first principles thinking perspective, we have labeled the protocols in layer 1, layer 2, and layer 3 very specifically. So layer 2 is the base or trust spanning protocol, what we've talked about so far, as with DIDCOM as a candidate. But on top of DIDCOM, it's a specific design, architectural and design point, is the ability to create what I call super protocols. Sometimes they've been called co-protocols, but I'm calling them super protocols. They're layer 3, they're application specific, they're business requirement specific protocols that are built on top of the base protocol. So layer 3 super protocols are built on layer 2 base protocols. And as we've seen in some of the examples, we also use that trust spanning layer protocol to talk to DID registries for doing DID resolution. And we also have DIDCOM agents talking to DIDCOM network message routing agents. So there's a concept of not only supporting applications up in layer 4, but also being able to reach down into layer 1 into the trust spanning, or excuse me, the trust foundation layer using the same protocol. So we're talking about an architecture in Web 7.0 where the trust spanning layer protocol is ubiquitous across everything. There is no other protocol. And the protocol of choice is DIDCOM. Let's go into that a little bit more. So here's the Celtic Tree of Life trust spanning layer model. And the idea is that the trunk of the tree represents the narrow waist of the hourglass model, on the hourglass model. And the roots, the bottom of the tree, represents the foundation. And as we know, the nutrients and moisture and actually oxygen flows into those roots in the foundation, flows up the tree to give life to the upper parts, to the branches, to the leaves and the fruit that grows on the tree. So we think of that trunk as the choke point. We think of it as the neck of the hourglass through which all communications flows. And of course, that's what we call our base protocol. Layer 1, the trust foundation layer, is where all the foundational infrastructure, resources, and services live. Things like the DIDCOM network and things like the DID registry. Layer 3 are the trust task layer, corresponding to the same layer 3 in the trust over IP trust spanning layer model. And to contrast those with the sub-protocols that are used to reach down into the foundation, as we're reaching up here towards layer 4, the trust agent layer, we call these super protocols. So super protocols reach up and sub-protocols reach down. And so the last layer is the trust agent layer. So these are where this is the application layer. These are where the trust agents live, in this case, the DIDCOM agents. Everything in Web 7.0 is a DIDCOM agent. There are no websites, there's no other kinds of apps. They're all DIDCOM agents, and they live in the DIDCOM trust agent layer. So let's start drawing some protocols. So we have what we call, as I said, the concept of layer 3 super protocols. These are for agent-to-agent messaging. These are for agents living in layer 4 to be able to talk to each other and to themselves. And so we've already seen in the DIDCOM agent model those purple boxes on those interfaces at the bottom of each agent. There's the outbound messaging or outbound processing interface. We talked about message transports for communicating or transporting messages between two agents. And then we have the concept of inbound messaging or inbound processing, where the receiver agent is receiving those messages being sent by the sender agent. So this is one type of protocol, which we call layer 3 super protocols. The other category of protocol are called subprotocols, layer 1 subprotocols. These are the ones that the trust agents in layer 4 use to talk to the foundation, to talk to the infrastructure services, to talk to things like DID resolution and for performing network routing. The support for offline trust agents that I described before is handled in layer 1, and so it's a layer 1 subprotocol that's used to interact with those. If you're familiar with the concept of just formal concept of DIDCOM protocols, which are application or business specific protocols built on top of the DIDCOM base protocol, both super protocols and sub protocols are DIDCOM protocols. But we're differentiating between super protocols that are used just for agent to agent transfer from sub protocols which are used to interact with the foundational services, the foundational infrastructure pieces. So if we superimpose these on the same slide, we can see what we effectively have, the formation or the hinting of a trust spanning layer protocol, because we are using the same protocol everywhere, the same DIDCOM protocol everywhere. And so if I was to put our layer 2 trust spanning layer base protocol box back on here, it's still the trunk of the tree, and it's the trunk of the tree that supports agent to agent transfer, which makes sense. All the branches come together at the top of the trunk. The message transport at the top of the trunk will exchange those messages with other branches of the trust agent layer. And similarly, when those trust agents running in layer 4 need to access infrastructure or foundational services in layer 1, they're also going to use that same trust spanning layer protocol, the base protocol for doing their work. I think you're starting to get a hint of where I'm headed. Just a comment on this design, and it's a feedback or reflection on one of the earlier protocol or proposals. And it was suggested that the scope of the work should be limited specifically to the layer 2 trust spanning protocol layer. And I disagree with that. Part of the post-proposal analysis and consolidation that we're about to undertake will require some of the perceived layer 2 base protocol capabilities described in proposals 1, 2, and 3 to be relegated or delegated either upwards to the layer 3 or downwards to layer 1. This relegation or delegation activity needs to be in scope for what the task force is undertaking. Further specification of what the details of those layer 3 super protocols and those layer 1 sub protocols can be deferred if desired to a separate work group or task force activity. But you need to have a very broad sense of system thinking applied here. You need to have a complete vision of the system platform you're building. In this particular task force, you may choose to focus on layer 2, but it's not to the exclusion of layer 3 and layer 1. So let's start to reflect a little bit on some of the proposals we've seen to date and Let's use that to lead us to a more detailed explanation, a more specific explanation of what the trust spanning layer framework that's being proposed in Proposal 4 actually looks like. So the inspiration for this entire Proposal 4 comes from this slide in Daniel Hardman's deck. Daniel is spot on in terms of the different kinds of capabilities that are needed in the trust spanning layer protocol. But what disturbed me is that it's very different from the approaches that were used to define the ISO OSI networking model. Daniel's showing a lot of stuff here in layer 2, a lot of functionality, and his presentation here, while good, it differs from my approach where I'm really focused on the needs of software architects and developers. And this was admittedly, highly conceptual and highly abstract, but it bothered me in terms of the complexity of these 5 categories. So I went back to something that Sam Smith had put together, the black and white drawing in the background, and I did some sketching on it. Sketching to show all the red sender-receiver interfaces that are part of the ISO OSI stack. And in particular, it reminded me that when the original designers of the OSI model came up with the stack, the transformations that happened in any particular layer, the physical layer, the data link layer, were very small, very clear, very small, very easy to understand. And I superimposed this with a diagram from Wei Jing's Proposal 3, because I think he did a great job of talking about this very point. At the top, we start with some application data in the application layer, and as we send it down on the outbound side, on the left, we're adding headers. And we're adding relatively simple headers as we go from application data to application type transports to the TCP and UDP transport layers, the internet transport layer like the IP protocol, and then finally down, to the link layers and the physical layers. So as we go down the left side, line number 1 there, it's the simple wrapping or encapsulation of the application data. And as we ascend on the inbound side, line number 11 there, what we're doing is each of those lower layers needs the information in its respective header, but once it has extracted that information, it removes that header until we're finally delivering application data to the applications. So very simple transformations of the data. And this helped me recognize that this was a design point, perhaps an unknowing design point, of the Web 7.0 DIDCOM ARM. And so we're going to explore how the Web 7.0 and the DIDCOM ARM processes messages, how it processes messages in those purple boxes that are part of the origin interface and part of the service endpoint. So here's a diagram. This is the verifiable credential sender receiver model that we looked at the end of the examples. And what I've tried to do here is elaborate on what are the developer level steps that happen or need to have happen in the purple box on the verifiable credential sender side, and in the purple box on the verifiable credential receiver side. So let's look at the sender side. So here we're expanding, what happens in the purple box on the origin interface, on the outbound processing interface. And this is the the state of the model before I started working on Proposal 4. With some coaching and back and forth bantering with Daniel Hardman, I've elaborated on this model, but to show a little bit of chronology, I want to start here. So to send a credential, we have steps S1 through S5. We create the credential, we sign the credential, we create a message and address that message. We auth encrypt the message and the verifiable credential if there's one, and then we send it. We send it to the receiver. On the receiver side, we receive the message, we decrypt the message, we verify the sender, we detach the verifiable credential, we verify the verifiable credential, and then we process the message and the verifiable credential through a business process workflow. Some very simple steps. Some very simple steps in contrast with the larger, richer set of 5 categories that were in the Proposal 2 trust spanning layer. Here's what I call the full meal deal model. This is the model I've come to more recently by looking and trying to mimic what Daniel is doing with his 5 categories. And so we see here that there's now like 8 steps on the sending side, and there's 6 steps on the receiving side. I've reordered the steps on the receiving side so they go from the bottom up. R1 is at the bottom, R6 is at the top. And I've tried to color them so that the actions or the operations that happen on the sending side can be visually correlated with the corresponding actions on the receiving side. You'll also notice that there's a box, a footnote in the bottom right-hand corner that said italicized steps. Italicized steps are optional. And we can see that most of the stack, most of the trust spanning layer protocol on the sending side is italicized. And similarly, if you're going to make it optional on the sending side, you need to make the corresponding operations on the receiving side optional. We have to specify those in italics. So let's start on the outbound side, sending a message. So S1, we create a message and whatever metadata needs to be associated with it. S2, we add a correlation ID. Daniel called this a thread ID. The correlation ID is more general because it not only needs to correlate like conversational threads, but it also needs to provide correlation across executing workflow instances. So for example, a request for quotation business document might come in as a DIDCOM message, and that's going to kick off the beginnings of a procurement workflow. As subsequent messages come in for subsequent steps in the procurement workflow, we need to make sure that they're all processed by the corresponding workflow instance, the workflow instance that was created when the initial request for quotation came in. And so the correlation ID is used for a workflow correlation ID. It can be used for chat correlation ID. It can be used for email conversations correlation, etc. So that's step S2. S3, of course, we have to address the message. We create the message and we address it. S4 and S5, we create the credential and we sign the credential. This is assuming that our business process, our business protocol, our application level protocol, our super protocol uses credentials as part of its message format. We attach those verifiable credentials to the message in step 6. In S7, we're going to auth encrypt the message and any embedded credential attachments. And then we're going to send those messages along with those embedded encrypted attachments if there are any. So S1 through S8 is the purple box on the outbound interface of the DIDCOM agent. And then we choose whatever transport, REST over HTTP, Bluetooth, whatever is appropriate for your platform. And we receive the message on the receiver DIDCOM agent on the left. the message receiver. So to receive that message, we receive it. We physically have an HTTP handler there that accepts it, receives it, and accepts it. Then we need to decrypt that message. We need to verify the sender. We need to detach the verifiable credentials from the message. We need to verify the verifiable credentials. And then finally, in step 6, we need to process the message, the metadata, and any verifiable credentials or other attachments that might be there. Again, I tend to talk specifically about verifiable credentials, but this could be California MDLs, this could be PDFs, this could be Office documents, this could be UBL, business language XML documents. And we process in step 6, we process the message and the metadata based on the current state of the process workflow instance. So if there is a non-zero correlation ID, it means that there is an existing workflow state and workflow instance that is ready and to be reconstituted to process this incoming message. If the correlation ID is 0, it means there is no overarching business process or workflow, and it's just an incoming message. Suppose, just for the sake of things, we get rid of all the italicized, we get rid of all the optional pieces. What do we end up with? We end up with the world's simplest trust spanning protocol layer. We create the message, we address the message, and we send it. We receive the message and we process the message. So if on the first slide, the previous slide, the pendulum is swung to the far left and we're showing all of the operations, all the potential actions that can take place in the outbound processing purple box, as well as all the inbound processing steps in the inbound processing purple box. Here we're showing the minimal amount. And so to address Daniel's proposal 2 idea, where there's these 5 different categories of processing that can take place, I think between this slide and the previous slide, we have a framework for embracing those ideas. I think on the previous slide, where we had the 8 outbound processing steps and the 6 inbound processing steps, we've probably captured 80% of what Daniel was talking about in that slide. And so we have a framework now for mapping a large number of the requirements illustrated in Proposal 2 into something that I think is more direct and more understandable by software architects and developers. But in the end, what have we done? All we've done is come back to this idea of the verifiable credential sender-receiver model. All we've done is elaborate on what happens in the outbound processing box, purple box, and the inbound processing purple box. So this is the most basic, this is the most simple answer to the trust spanning layer protocol question. Let's take this layer 2 discussion of this base trust spanning layer protocol and look now at a discussion around level 3 layer 3 super protocols and layer 1 sub protocols. Layer 1 sub protocol. So here the examples are going to be DID resolution gateway agents and DIDCOM intelligent network routing agents. So let's bring back this picture that we looked at before. So remember, layer 1 sub protocols are how trust agents running in layer 4 interact with the foundational services. I've chosen to highlight DID resolution and network routing, but any foundational service, maybe there's a payment gateway. A payment gateway would be a foundational service. And so it would have a trust spanning subprotocol defined for it, and trust agents running in layer 4 would use that payments subprotocol, for example, to access the payment service. So let's again look at those examples. So we've actually seen this one already. This is the DIDCOM network router agent example. So the two DIDCOM message routes, the two purple lines, the one that goes into the green box and the one that leaves the green box, those are examples of layer 1 subprotocols. And in particular, this would be the currently specified, or a variation of the currently specified DIDCOM forwarding protocol for forwarding messages through a network or a sequence of intervening DIDCOM agents. In the current, I believe, V2 specifications, you need to pre-specify what that route is. The innovation here in Web 7.0 and the Web 7.0 DIDCOM network is that you just need to fire off the message wrapped in as a forwarding message into the network, and the network will look after the intelligent routing and deliver it to Bob's agent. And of course, Bob's agent is the only agent that can decrypt and inspect that message, because when Alice created it on the right, she used Bob's credentials to create that message. And then it subsequently wrapped it with the forwarding wrapper. So this is the simple view of the layer 1 subprotocol example, the DIDCOM network router agent. We've seen the kitchen sink model already. This is just embellishing on the fact that we can evolve or adapt the network from being a single relay agent, as we've seen on the previous slide, to a global network of message passing and delivery agents. There could be hundreds, thousands, tens of thousands of DIDCOM network router agents running around the world. This is the DIDCOM registry agent example. So here in the blue box, we see that Alice's DIDCOM agent is executing a DIDLang query over DIDCOM to query the DIDCOM registry agent gateway. And Alice's agent is using DIDCOM for that, just like we would expect in Web 7.0. And it's the role then of that DID registry gateway to use the DIDLang over DNS protocol to access the DID registry just above the blue box, using whatever its native protocol is. If you want to use the DID resolution over HTTP protocol and build a custom DID resolution over HTTP server as defined in the DID resolution specification, you can do that too. We would still wrap it with a DID registry gateway so that those DID resolution over HTTP queries and responses are mapped into DIDCOM queries and responses. To see a slight elaboration on this example and to reintroduce the concept of the SAM stack, the Sam Smith stack. This is going back to the hourglass model, and we can see at the top we have different kinds of agents, 4 different kinds of agents in Web 7.0, and they're reaching down using that communication path number 9 to the DIDCOM registry gateway. So number 9 is an example of a layer 1 subprotocol. It's the DIDLang over DIDCOM, DID query, and DID document response path. And the other things that are in the layer 1 trust foundation layer to the right of the DID registry gateway are other kinds of DID registry servers that are in the background that are actually serving up the DID document data. and they're chained together using their native DNS protocol. But all of that is hidden. All of that is hidden behind the DID registry gateway, and so we can still say that Web 7.0 and the Web 7.0 trust spanning protocol is DIDCOM, DIDCOM, and DIDCOM. Okay, so we've used two examples to illustrate what a layer 1 subprotocol is. Let's look at layer 3 super protocols. Layer 3 super protocols are for trust agents running in layer 4 to talk to each other. And I think more people will be more familiar with this form of agent-to-agent messaging. So Daniel Hardman, in one of his video tutorials, talks about DIDCOM protocols, the DIDCOM protocols in the formal sense, which are those application-specific or business application-specific protocols that are built on top of the DIDCOM-based protocol. And we see some of them here to support voting, to support hailing a taxi, to support booking a hotel. Filing an insurance claim is a nice example of a business process. Negotiate price and payment, which is really a procurement type of scenario. So these are what Web 7.0 refers to as layer 3 super protocols. And we have a very specific definition of what a super protocol is. Some of the details here may surprise you, but again, this is an example of first principles thinking applied to layer 3 super protocol definitions. So there's a number of different things. I think it's 5, maybe 6 components that actually define a layer 3 super protocol. And the first one, of course, is there's going to be process or application or business-specific message formats and schemas. Application or business process-specific DIDCOM message formats and schemas. There's also going to be, those message formats may also define or require by reference certain types of message attachments. So there will be process-specific or perhaps generalized standards like the UBL specification for defining message attachments. The MDL specifications for California driver's license fits into here. Those specifications of these message attachments wouldn't be included in your layer 3 definition, but they would be referred to by reference in a layer 3 super protocol definition. If there are very specific new formats, they may be defined as in line, if you will, as part of your layer 3 super protocol definition, but hopefully they're defined externally to enable reuse. The third component, which may surprise people, is that a layer 3 super protocol can optionally define a specific executable business process workflow template. And the intent here is that when a message of a particular message type containing an attachment of a particular attachment type is received by a DIDCOM receiver, that DIDCOM receiver can know what business process, what programming is to be applied to that incoming message. The idea in the fullness of time in Web 7.0 is that all executable logic, all programmability of a DIDCOM agent will be defined as a business process workflow template. And the suggestion here and the direction for the initial release of Web 7.0 is to use the OASIS BPMN process workflow template standard that is serialized using the OASIS BPMN defined XML serialization format. So we have a lot of good standards that are working together. The idea of unification, the idea of having a unified platform. Of course, governance is always a key aspect of any good solution. So additional governance such as the specification of business rules, policies, procedures, and other process documentation. Hopefully as much of this as possible is implemented in the business process workflow template. A colleague recently commented, well, if an incoming message is of the wrong format and you send it into the workflow, isn't that going to break the workflow? No. The first couple steps, the first couple tasks of any business process workflow template should be tasks to validate the input. We should use the business process workflow template for implementing governance and implementing normal quality assurance steps dynamically on the incoming data as messages are being received by a DIDCOM agent. Lastly, there's the scenario where a DIDCOM message may reference an external attachment as an alternative to having an embedded attachment. If a DIDCOM message has an embedded attachment, then its trust, security / privacy policies will be the same as the message, because the message, the way the message is processed through the outbound processing stack and the inbound processing stack, whatever happens to the message is going to also apply to the attached the attached embedded attachment. But we need a special set of trust, security, and privacy policies for external attachments that we are referring to by reference. This is another example, if you will, of a layer 3 super protocol. This is the four-corner interoperability model. So one problem that has not been solved in the W3C, and they're actually staying completely away from it, and hasn't been solved anyplace else, is the idea of enabling ABC Grocery and David's Cabbages to use different credential formats, different, for example, verifiable credential formats. So in the green box on the right, we see ABC Grocery is sending a purchase order credential from ABC Grocery's software agent, DIDCOM agent, over to David's Cabbages DIDCOM agent. So suppose ABC Grocery wants to order 10 cabbages from David's Cabbages. Well, ABC Grocery's internal system, line of business application, ERP system, procurement system, uses a different credential format. Let's say it's called VC. In the purple box on the left-hand side, David's Cabbages uses a different accounting system, a different procurement system, a different ERP system, and it uses a format called LDVC1. So how do we rationalize that? How do we make it work? So there is an a specification called the Web 7.0 intercredential or Internet Credential specification that talks how the four-corner interoperability model works. I owe Ken Holman credit for this. He's been talking about this, and it's a solution that came from the UBL community, the Universal Business Language community, who is facing and addressing real-world problems with the exchange of 91 of the most common business documents. So this is an example of a fairly substantial, fairly innovative layer 3 super protocol. This is an elaboration on the four-corner interop model. It's probably out of scope for this presentation, but the slides in here. We've already talked about embedded attachments versus external attachments. In the case of external attachments, where the bytes are stored externally, let's say in IPFS, you need to be able to specify as part of your protocol what those bytes look like on IPFS, how they're encoded, how they're encrypted, how they're secured from a security, privacy, and trust perspective, that's not a layer 2 responsibility because it's not part of the base protocol. What is part of the base protocol is the handling of embedded attachments, because we're just saying that the trust, security, and privacy policies of embedded attachments are the same as the containing message. But when we talk about external attachments, we actually have to treat external attachments using a layer 3 super protocol, because we need to be able to specify that additional information, the additional trust, security, and privacy policies that apply independently to that external attachment. So when we're dealing with external attachments, that's an example, an interesting example again, of a level 3 super protocol. This brings us almost to the end. Again, there was some work completed on February 24th. Initially, Brian Richer had added some comments alongside the 18 requirements that have been specified for the trust over IP trust spanning layer. And Daniel Hardman then added his comments alongside Brian's. And I helped format some of those results and give people a nudge to get things done. And so here, it's a bit of an eye chart, but we can see Brian's comments there in the 4th column, and we can see Daniel's comments in the 2nd column. And if you scan down, we see that we have affirmative answers in terms of DIDCOM v2 meeting or exceeding the requirements as laid out by the ToIP technical architecture specification. And the overall assessment is in the rightmost column. We can see for the first, 9 layer 2 requirements that DIDCOM does meet or exceed every one of those 9 requirements. When we look at requirements 10 through 18, we similarly find affirmative responses from Brian and from Danielle in terms of DIDCOM's ability to meet or exceed the requirements 10 through 18. So the overall assessment then is DIDCOM Communications does meet or exceed the overall requirements of the trust over IP technical architecture specification layer 2 trust spanning layer requirements. We've also shown up to this point in the presentation that DIDCOM in and of itself is an incredibly awesome trust spanning layer protocol that you can build an entire platform, including DID resolution, including DID registry queries and responses, including DIDCOM network routing. DIDCOM is an incredibly powerful protocol. And if you think back to Sam Curran's comments from the very beginning of the deck, that we need to focus on specifications, on capabilities, on protocols like TCP/IP and protocols like DIDCOM that are open to innovation and enable things like Web 7.0 to be easily built in a highly unified end-to-end way. So just to wrap up here, this is a little bit of a throw-in, but this idea of having a unified end-to-end single spanning layer protocol architecture reaps additional benefits besides the obvious ones that we've been talking about or assuming when we talk about trust spanning layers and trust spanning layer protocols. One example in Web 7.0 is the fact that we can use automatic agent code generation to generate all the different kinds of DIDCOM agents that we need. Remember, we have generic DIDCOM agents, and then we have specializations, the DIDCOM registry gateway, the DIDCOM network message routing agent, and the DIDCOM user agent. They're all specializations, they're all derivations of the same common DIDCOM agent architecture. And so we have a language we use in Web 7.0 called TSL, the Trinity Specification Language. It comes from a Microsoft research project. And I'm just going to highlight briefly how we've been able to super leverage the DIDCOM protocol and the Trinity Specification Language to make a very powerful automated code generation system for Web 7.0. So at the bottom here, we're defining a server. We're defining a DIDCOM agent. And we say that it has one service endpoint called the DIDCOM endpoint. We can see that that DIDCOM endpoint is defined as being an HTTP endpoint, and it has a request message, and it has a response message. The request message in blue is defined in lines 23 to 26. We see that it's a DIDCOM encrypted message. The DIDCOM response could be defined in TSL as a void, as shown in the comment, but in this particular case, we've just chosen to return an integer return code. This is probably not compliant, 100% compliant with the DIDCOM spec, but we use it for internal debugging and tracing and that sort of thing. So things work very well when you have this uniform trust spanning layer protocol that's used for all the super protocols and all the sub protocols across the entire platform. Just one last example as we close off this deck. We can also define DID documents using the TSL, the Trinity Specification Language. And here, directly out of the DID core specification, you can look at the DID document properties for a DID document. And they're defined here in lines 45 to 58. We have a string ID, we have the context, also known as the controller, defined as lists of strings. We have verification methods and assertion methods and capability delegations. They're all defined as lists of verification method maps. And at the bottom, we have the service endpoints. We have the service node, and it's defined as a list of service maps. And if we look up above in lines 33 to 39, that's what a service map looks like. It's an ID and a list of types and a list of service endpoints. If we go up and look at lines 24 to 31 to see what a verification method map is, and a verification method map is a formal name taken right out of the specification, the URL on line 23. We can see that a verification method map has an ID, a controller, a type, a public key multi-base string, and then it has a JSON key map. This is automatically processed every time we build a DIDCOM server to automatically build all the classes, all the methods, all the processing, all the automatic persistence that we need, persistence, serialization, and deserialization that we need to rapidly build DIDCOM agents of any flavor in Web 7.0. Okay, this has been a little bit of a fire hose. We're up to about an hour and 20 minutes, but I hope you found it useful and highlights not only what I believe are the goals of the Trust over IP Trusted Spanning Layer Protocol Task Force, but also highlights how DIDCOM is a perfect solution in terms of meeting the requirements, and a perfect solution for building entire decentralized systems platforms using the DIDCOM protocol. If you have any further questions, you can tweet them to Freddy Architect on Twitter. Freddy's always available to help you and answer your questions. Thank you again for listening to this and watching this presentation. I hope you found it useful.